Excel tutorial, probability distributions. Probability distributions consist of all possible values that a discrete or continuous random variable can have and their associated probability of being observed. Classical or a priori probability distribution is theoretical, while empirical or a posteriori probability distribution is experimental. This topic is part of Business Statistics with Excel course. Feel free to take a look at course curriculum by clicking link at description box below. This tutorial has an educational and informational purpose and doesn't constitute any type of forecasting, business, trading, or investment advice. Please read full tutorial disclaimer at the end of this video. Normal probability distribution consists of all possible values that a continuous random variable can have and their associated probability of being observed. Its probability distribution function is bell-shaped, symmetric from its mean, and mesocurtic. Standard normal probability distribution consists of normal probability distribution with mean zero and unit variance. Any normal probability distribution can be converted into a standard normal probability distribution through continuous random variable standardization. As a formula, normal probability distribution probability density function is equal to 1 divided by the square root of 2 times pi, which is then multiplied by sigma squared. Sigma corresponds to the continuous random variable standard deviation, therefore sigma squared corresponds to its variance, which is then multiplied by the exponential of minus, and within the numerator we have x, which is the continuous random variable, minus mu, which is its arithmetic mean, that result to the power of 2, which is then divided by 2 times sigma squared. And then to the left we have that the normal probability distribution mean equals to mu, and to the right we have the standard normal probability distribution mean equals to 0. To the left we have normal probability distribution variance equals to sigma squared, and to the right we have standard normal probability distribution variance equals to 1. Both normal and standard normal probability distributions have skewness equals to 0. Both normal and standard normal probability distribution have excess kurtosis equals to 0. And then we have set, which corresponds to the continuous random variable standardization, which is equal to, and within the numerator we have x, which is the continuous random variable, minus mu, which is arithmetic mean, and that result is then divided by sigma, which corresponds to its standard deviation. Great, so let's go into our Excel file so that we can study normal probability distribution with greater detail. Perfect. So here we are within probability distributions Excel file, and within this tutorial we'll be working within the orange colored probability distributions worksheet. So first of all we have the data, which is found at columns B and at column C. At column B we have dates with a daily frequency, and we see that they're from the beginning of 2007, and we select B4 and press Ctrl down arrow, we go into the end of the column all the way into the end of 2015, therefore 9 years of data. So we press Ctrl up arrow, down arrow 2 times to go into the beginning of the column. Then at column C, with a green color background, we have SPY adjusted close prices. SPY corresponds to the ETF investment vehicle, which intends to replicate the Standard & Poor's 500 index, and adjusted close prices because they were adjusted for dividends and splits. So the following step is at column D, we're going to calculate the daily arithmetic returns of those SPY adjusted close prices. Notice that the first return here is found at D4. It has an orange color background to distinguish its calculation with the rest of the column, and here we include 0%. This was included as an educational example, therefore it is not fixed, and it can be modified according to your needs. The reason we have that first cell with a 0 is because we need at least 2 prices for the calculation of the first return, which is what we do right here at D5. So for the arithmetic return, as we can see here, it's equal to C5, current day price divided by C4, previous day's price, and that result minus 1. If we select here D6, we see that it's equal to C6, current day price divided by C5, previous day's price, and that result minus 1, and so on for the rest of the column. The following step is we're going to standardize this corresponding arithmetic returns, and we do so at column E. So here we select E4, and we see the built-in Excel function of standardize, and here we have D4, which is the corresponding arithmetic return, comma, and we include for the arithmetic mean the built-in Excel function of average from D4 to D2269. So we're selecting the full column of daily arithmetic returns. Notice that these cells, the beginning and the end of the range, have been fixed. That's done by adding the $sign before the column and before the row, and that can be done by pressing F4 on the keyboard or adding them manually. This is done so that we can copy this formula down for the rest of the column. Comma, and for standard deviation, we're using sample standard deviation with the built-in Excel function of stdb.s, also from D4 to D2269, again, this value is being fixed. So just double checking, we select D4, the first arithmetic return, control, down arrow, we go into the end of the column. At D2269, we see the last of these arithmetic returns. So we press control up arrow, down arrow, again to go into the beginning of the column. So going back into that calculation, we see standardized of D4 and then the corresponding arithmetic mean and sample standard deviation. And if we select the following cell at E5, we see standardized of D5 instead of D4, but these two remain the same, the average and the sample standard deviation, both of them from D4 to D2269. An important observation regarding this standardization of arithmetic returns is that, as we saw within the formula, we're first subtracting the arithmetic mean and dividing that result by the standard deviation. Therefore, they can be interpreted as a number of standard deviations from the arithmetic mean. So the following step is we're going to calculate the density histogram for these standardized returns. So first of all, we have a column F, the beans, and as we can see, these beans, which begin at F4, are from -11. Again, we're using number of standard deviations from the arithmetic mean, and if we press Control down arrow, it goes all the way into +11 at F26. So we press Control up arrow, down arrow 2 times to go into the beginning of the column. And then we have the standardized returns frequency. This is the absolute frequency. That's the number of observations at each of those beans. This was calculated previously to recording this video tutorial, and it was done using, within the Data tab, we have the Data Analysis Toolpack, and specifically the histogram tool. So with this, we can calculate the corresponding standardized returns density or relative frequency. Relative frequency because this is going to tell us the corresponding number of observations at each of those beans as percentage of the total number of observations. So if we select here H4, we see the calculation equals to G4, which is the corresponding absolute frequency for that bean, divided by the sum, again, being fixed from G4 to G26, so from the first of this absolute frequency to the last, and we are fixing it so that we can copy the formula down. So if, for example, here we select H5, we see instead it's G5, the corresponding being absolute frequency divided by the sum from G4 to G26, which is the sum of absolute frequency or the number of observations. So just double checking this calculation, we select H4 and press Ctrl Shift down arrow for selecting the full column, and we can see right here at the bottom that the sum is 100% as expected. So we will press up arrow, down arrow to go into the beginning of the column. The following step is we're going to calculate the density or relative frequency histogram for the standard normal probability distribution. So the first of this is right here at I4, and we see within the formula bar that it's equal to normal.s standard normal.this distribution of F4, which is the corresponding bean, comma false because we want it cumulative equals to false. So if we select I5, we see the same norm s.this, but instead with F5, which is the corresponding bean. Again with false, cumulative equals to false. So we select here I4 and we press Ctrl Shift down arrow, again double checking, and we can see the sum equals to 100% as expected as well. So we press up arrow, down arrow to go into the beginning of the column. So the following step is we're going to calculate some descriptive statistics for the standardized returns. So the first right here at L3 is the sample mean. So we're using the built-in Excel function of average from E4 to E2269. So the first of those standardized returns. So we select it here, just double checking, and we press Ctrl down arrow. We see it goes all the way into E2269. So again, we press Ctrl up arrow, down arrow to go into the beginning of the column. Then we calculate the sample standard deviation at M3, and we're using the built-in Excel function of stdb.s from E4 to E2269, again, that same column. Then we have sample skewness at N3, which is equal to the built-in Excel function of skew from E4 to E2269, again, the full column of standardized returns. And last, we have the calculation of the sample excess kurtosis at O3 with the built-in Excel function of KURT for excess kurtosis, and here we have it from E4, the first of the standardized returns, to E2269, the last of them. So looking at those descriptive statistics, first of all, we have for the standardized returns, as expected, both the sample mean equals to 0 and the sample standard deviation equals to 1 as expected because of the standardization. So notice we're calculating descriptive statistics for the standardized daily arithmetic returns. And something very important here, we see that the sample skewness was positive and also the sample excess kurtosis was positive. So the following step is we are going to compare the standardized returns density histogram with a curve overlay with the standard normal product distribution, which is what we have here within the chart. So we're going to zoom out, in this case to 120%, so that we can see it in a full size. And we have within this chart, as mentioned within the title, the standardized daily arithmetic returns density histogram. On the vertical axis, we have density or relative frequency, and on the horizontal axis we have the corresponding beans. So the relative frequency is the number of observations as percentage of the total number of observations at each of those beans, and the beans as a number of standard deviations from the arithmetic mean. So as we can see here with the legend and here colored in blue, we have the corresponding columns of the density histogram for the standardized daily returns, and then we see colored in orange on top of it the curve overlay for the density of the standard normal product distribution. So what we can see here is we are corroborating the results specifically for the descriptive statistics of the sample skewness and the sample excess kurtosis, and we are corroborating it visually because we see that those standardized daily arithmetic returns had positive skewness and had positive excess kurtosis. But as you might remember from the slides, the standard normal and the normal product distributions, they have skewness equals to 0 and excess kurtosis equals to 0. So first, looking at the sample skewness, we see that the standardized daily arithmetic returns had positive skewness, and that's what we can see here as the corresponding blue colored bars have that positive skewness, therefore extending towards the positive values. And we can also see that they had the positive excess kurtosis, and by comparing the corresponding bars with the curve overlay, as we did with the corresponding sample skewness, we see that the blue colored bars were more peaked and with thicker tails compared with the standard normal product distribution, therefore corroborating both of these results in a visual way. Excellent. So now that we've finished studying probability distributions, specifically the normal probability distribution, let's go back into the slides. And as mentioned previously, this tutorial has an educational and informational purpose and doesn't constitute any type of forecasting, business, trading, or investment advice. Please pause the video now so you can read the full tutorial disclaimer. Okay, so with this we finished this tutorial. Thank you for watching.